root functions, nth root of x. So root functions are nth root of x where n equal to 2, 3, 4, etc. So where is it continuous? For example, if n is 2, 4, 6 even numbers, then the graph of nth root of x looks like this. Nth root of 0 is 0, and it looks like that. Right? So where is it continuous? Well, at this point C, its limit value is equal to its function value, so it is continuous. How about 0? So if f of x equal to nth root of x, then f0 is 0, so it is defined. So 2 is fine. How about 1? What was 1? 1 was the limit x approaches to c f of x. We have seen this before, that if we have square root of x, for example, the limit does not exist as x approaches to 0 because we are approaching 0 from both sides and there is no function. So limit does not exist. So 1 fails. Right? So f is not continuous at 0. But any number bigger than 0 is okay. Whereas, if I look at odd roots, for example, cubed root of x, then its graph looks like, for example, cubed root of minus 8 is minus 2, so it is defined at negative numbers and it looks like this. So for odd roots, it is continuous at 0, continuous at c positive, continuous at c negative. Its function value equal to its limit. So for odd roots, it is continuous everywhere. Okay. So where if n is even and 2, 4, 6, etc., continuous at x bigger than 0. If it is odd numbers, then for all real number x, it is continuous. Okay. And for even numbered roots, even if I cannot say, for example, I cannot say square root of x is continuous at 0. I cannot say this because I cannot approach 0 from the left. But what I can say is the following. See, if I take limit x approaches to 0 plus from the right of 0, then this limit exists and is equal to its function value. So I can say square root of x is continuous from the right at 0. Likewise, I can say nth root of x where n is 2, 4, 6, etc., all even roots. I can say nth root of x is continuous from the right at 0 for n equal to 2, 4, 6, etc. Continuous from the right. So that is the definition for conti from the right at 0. So we say if limit x approaches to c plus f of x equal to f of c, we say f is continuous conti from the right at c. Now if it is c minus, then we say f is conti from the left as c. F e to the x. What was the graph of e to the x? Yep, it looks like this, yep. So at any point c, its limit is equal to its function value. So e to the x continuous at all real numbers. ln x, what was the graph of ln x? That was the mirror image about the line y equals to x. So it looks like this, yeah. So for ln x, any c bigger than 0, the function is continuous. So at any x bigger than 0, ln x is continuous. And then sum and difference, product, quotient, and a constant multiple of continuous functions. Where? Okay. So for this, suppose f is like this. What does this tell you? It tells you that f is, this means i.e., in other words, f is conti at c. And suppose limit g of x is also g of c. In other words, g is conti at c. Suppose I have these two. Then if I look at limit of the sum, f plus g at x is, how do we do f plus g at x? You do f of x and g of x. So you evaluate f and g at each x and then add their output. That's what f plus g at x means. And now limit of f is, does the limit exists? Yes. F is continuous as c, so limit exists. How about g? Does the limit exist? Yes, because g is continuous as c. That was condition 1. So limit exists. So by limit law, limit of the sum is sum of the limits. So that is this plus that's this. Now, what was this? Yes, by continuity, limit of f was f as c. By continuity, limit of g was g as c. So, by continuity of each of, by continuity of f and g individually, right, we get f as c plus g as c. And this is nothing but the sum evaluated as c. So we started with this limit of f plus g at x, and we ended with f plus g as c. Therefore, f plus g, this function is continuous at c. So, if both f and g are individually continuous at c, then its sum is also continuous at c. That was by limit law. So since we have limit laws for sum, difference, product, quotient, and a constant multiple, by similar logic, we can say if f and g are individually continuous, then at those points, its sum, difference, product, quotient, and constant multiple is also continuous. And for quotient, we have to say the denominator is not 0. Okay, so where f and g are continuous. And for quotient, we have to add in g's of c not 0. So for example, suppose I want to find the limit x approaches to 0 of sine x plus x squared. So sine is a trigonometric function, canti everywhere, and x squared is a polynomial, continuous everywhere. So since individual functions are continuous, their sum is also continuous. So by continuity of the sum, I can plug in the value directly. I can do direct substitution. Sine 0 is 0, 0 squared is 0, so we get 0. Okay. And H, F circle G. What does F circle G mean? So that's a composition. So it is f of g of x, right? So to have that continuous, it is conti if limit x approaches to c of f circle g at x equal to f circle g at c. That should be true. In other words, limit x approaches to c f of g of x equal to f of g at c. So to have this equation true, f should be continuous at g of c and g should be continuous at c. Okay, so where is it continuous? Where f is conti at g of c and g is conti at c. Then the composition is continuous. So for example, suppose I want to find limit x approaches to pi of e to the tangent x. So this is nothing but exp of tangent x. So I can think of this as f and think of that as g. So it's a limit of composition. Graph of tangent looks like this, yep. That's pi. So tangent is continuous at pi and exp is continuous everywhere. So this composition is continuous at pi. Therefore, I can do direct substitution. Since this composition function is continuous, I can plug in pi into x. So I get e to the 0, so it is 1.